I'm Diego Ochoa from Power Smart Control, and today I'm going to show you how to design the control loop for the three-phase Vienna rectifier. That is the new topology that we introduced in the new version of the Smart Control. So let's start with a brief introduction about Smart Control. Here. So Smart Control is a tool that allows to design in an intuitive and simple way the control loops of the power electronic converter. You can design the control loop for different topologies for DC-DC converter, the AC-DC, DC-AC, and AC-AC converter. This tool is very useful in different sectors, for example, such as in education, in industry, and in each and others sectors. Also, Smart Control adapts to different level of knowledge because there is a three-way that we can define the converter plan. I will show you a little bit what are the three ways. Once the control loop has been decided, the results can be exported directly to third-party simulators, for example, PSIM or Simba. Also, Smart Control allows you to design in continuous domain or Laplace domain in order to design the analog control, and also you can define some transfer function in C domain or discrete domain in order to design the digital control in that case. When we open the Smart Control software, this is the first window that appears, and here we can select different options. The first option that we can define the converter plant is called the predefined topology. As you can see here, we have different control structure. For example, you can find a single loop if you want only to control the output voltage or inductor currents. Also, you can find the control structure for the peak current mode control. And for example, if you have a double loop or average current mode control, also there is another predefined topology for DC-DC converter. In the case of the PFC rectifiers, we have two options. The first one is related to the single phase, and the second one is related to the three-phase PFC rectifier. In that case, in the new version of the Smart Control, we have two options in the three-phase rectifier. That is one of them is the two-level boost PFC rectifier, and the new topology that is the three-phase Vienna. So in that case, in the first way that we can define the converter plant, for example, if we select the DC-DC converter with an average current mode control, the next window that appears is this one, and here you can see the design flow of this control structure. So the first step, we have to select one plant here. You can find for the DC-DC converter, you can find plans for buck converter, boost converter, buck bus, flyback forward, dual active bridge, and the phase shift full bridge converter. After you select one of the plan, you have to define the sensor stage. This is the inner loop. For the inner loop, we are controlling the inductor current. So here we have a different predefined current sensor. One of them is the Hall effect sensor, and also you can find an option that's called equation editor for the sensor. For example, if you want to write your own transfer function or analytical transfer function of your sensor, the inductor current sensor change, for example. After that, we have to select one option of the compensator stage. In Smart Control, we have three predefined compensator, the type 2, type 3, and PI. And also you can find the option that's called equation editor again, that you can write your own transfer function of your own compensator. So in that case, Smart Control is very flexible in order to define the transfer functions. After that, in the right side of this window, you can find the solution maps. The solution maps represents the relationship between the crossover frequency and first margin. So in this white region, this is all the solution that Smart Control ensure that your PI or your compensator will be stable. So this is a very useful tool and very easy to use because you can just select one point of the solution maps. So after you select one point of the solution map for the inner loop, you have to define the sensor stage for the output voltage. In that case, we have also SmartCtrl has a different predefined voltage sensor. For example, you can find for a simple voltage divider, and also, for example, if you have a voltage divider and one pole, a low pass filter, for example, you can find here. And also there is an option, the equation editor, and you can write your own transfer function for the output voltage sensor chain. And finally, we have select one type of the compensator for the outer loop. After that, we have second solution maps. This solution maps is related with the bandwidth of the outer loop. So, and here you have to select one point of the solution map, and then you can see the transfer response of the some waveform of the control. So the second way to define the converter plan is called equation editor, and you can find in the national dialog in this section. This is the equation editor. And here you can write the transfer function of any of the power converter electronics. So here you have to model the converter, and you have to get the analytical transfer function, and then you have to write in this region in the equation editor. So the equation editor also accept transfer function in S domain for analog control, and also accept directly in C domain for digital control. You can write here discrete transfer function. So these options perhaps is necessary to have some experience in converter modeling. So the equation editor is available for the converter plan, also for the sensor stage, and for the compensator. So this is a very generic solution if you want to design a control loop for any type of power electronic converters. The third way, in order to define the converter plan, it's called import frequency response data from txt file. It's in this option. And here, for example, if you already have a schematic or a simulation, for example, from PSIM, in that case, you can use the function that it's called AC sweep in order to get the frequency response of the converter plan. In that case, this information you can save in a txt file, and then in SmartCtrl you can import directly from the txt file the frequency response, as you can see here. So this is a very useful tool. For example, if you have a real control, real converter prototyping, for example, you can measure the converter plan with a frequency response analyzer, and then you can import to a SmartCtrl. So in SmartCtrl, when any of the parameters are modified, all the results are updated immediately. So another tool that SmartCtrl has is a sensitivity analysis that is called parameter sweep. In that case, you can change the input values. For example, you can modify the input voltage, the value of the inductance, capacitance, or output voltage, for example, with the slider, or just by enter manually here in this edit text box. And you can see how, when you change this parameter, how the dynamic of your system is affected. So it's a very useful tool. As mentioned before, this is the solution maps. Remember that the solution maps represents the relationship between the crossover frequency and the phase margin. As you can see here, if you move the cursor through the white region, all the body plots and transient response and some waveforms are updated immediately. So after finally, when you already select one point of the solution map and you want to export the result, we have different options. One of them is called the report, and here you can find, for example, if you selected a type 3 compensator, and here you can see, for example, what is the frequency of the zero and the pole, etc. in that case. And also, if you implement in an analog with a passive components, the compensator, also you can find some suggestion about the value of the resistor and capacitance in that case. Another things that SmartCtrl can export is all the waveform. For example, you can export the body plots or returns response. You can export this information in a TXT file. If, for example, if you want to make a post-processed information later or something like that. And the last solution, if, for example, if you want to export the predefined topology to the third-party simulator for PSIM or SIMBA. In this moment, this option is available PSIM for all the DC-DC converters and three-phase PFC, and for SIMBA is just available for three-phase rectifier. Include the two-level boost PFC rectifier and the three-phase Vienna rectifier. So, in the installation folder of the SmartCtrl, you can find different documents. You can find a folder that is called example, and here there is a lot of tutorials. Inside each tutorial, you can find the PDF file. So in that case, in the PDF file, you can see step by step how to design the control loops using SmartCtrl for the different type of control structure. For example, if you want to design the control loop for the single loop, double loops, etc., the peak mode and mode control, digital control, etc. There is a lot of information inside this for each tutorial folder. You can find also the PSIM simulation file and also the SmartCtrl file that you can see where you can see the how we can tune the compensator. So also in the installation folder, you can find another folder. It's called docs. Inside this folder, you can find the SmartCtrl user guide, that is the user manual, and also another file that it's called the what's new. The what's new is related about what is the last feature that the new version of the SmartCtrl includes. So in that case, for the SmartCtrl for the 2025.1, this is the new version of the SmartCtrl. We introduce a new AC-DC converter topology, that is the three-phase Vienna rectifier. In that case, for the Vienna rectifier, also we can design the control loop in different domain. For example, you can select the control structure implemented in alpha-beta domain or in DQ domain. Also, in this topology, you can select different type of filter. For example, if the Vienna rectifier is connected with a simple L filter or LCL filter, maybe if you want to, implement a LCL filter with some passive damping, also there is an option. And you can take into account also the EMI filter for the Vienna rectifier. And in this topology also, you can design the new control loop that regulates the desync voltage balancing. Remember, because in this topology we have two capacitors and the output port. So, and also you can select one point of the solution maps. In this new version, now we can export the three-phase PFC rectifier for the digital case directly to PSIM simulator. So in that case, if you design the digital control, SmartCtrl take into account the digital delay, also the ADC gains, etc., and you can simulate directly to PSIM in that case. And this is for the digital control. This is available for the boost, the three-phase boost rectifier, and also for the Vienna rectifier. And in the analog case, we can export directly to PSIM and SIMBA both the the three-phase two-level boost rectifier and also the three-phase Vienna rectifier. So in this new version also include a new tools that it's called the system level stability analysis. This is, for example, when you put a EMI filter to the three-phase rectifier, there is a interaction between the two both subsystems, and this tool predict the stability of the system when you put the two subsystems together. So this is a very useful tool. I want to show you later with a live demo. And finally, in this new version, also we expand more tutorials, more videos in order to guide you how to design the control loops for using the SmartCtrl software. So this is the wise new. Here, this is related to the three-phase Vienna rectifier. As mentioned before, here you can see we have two capacitor in the output side, and we have the midpoint. This is related to the analog cases for the three-phase Vienna rectifier. You can export directly to PSIM and Simba. And also the digital cases for Vienna and three-phase boost PFC, you can export directly to PSIM. In that case, also the sensor chains contemplate the sampling instant, etc., the digital filter, and also we have some digital delay in these templates. Okay, so let me open the presentation. In this slide, you can find some links that take you to our YouTube channel. You can find all the webinar that we made in the past, and also we have some other resources with Altair. So in that case, you can see here in some video tutorials, you can see the link process between PSIM and SmartCtrl. So now it's time to start the live demo. In that case, we are going to show you how to design the control loop for the three-phase Vienna rectifier. That is the new topology that it's included in the SmartCtrl 2025.1 version. So the three-phase Vienna rectifier plays a crucial role in various applications like electric vehicles, chargers, grid energy storage, for example, some other applications. However, there is an interaction between the EMI filter and three-phase rectifier often leads to a system instability, posing a significant challenge in design and implementation. So I want to show you, for example, first I want to design the control loops for the three-phase Vienna rectifier. Then I put an EMI filter, and I want to show you how we can use the system stability system tool in order to predict the stability of the system when you put the EMI filter to the converter. So let's start. Now I will open SmartCtrl. So I go to File in that case, and if you can access to the initial dialog if you go to File and click on initial dialog. So in that case, we have the three-phase PFC converters option. You have to click here. And now we have here you can, in the single line diagram, you can select the different option or the different combination. For example, what kind of control structure do you want to implement? For example, you can select control for DQ control, the alpha beta plus proportional resonant current compensator, or alpha beta with a PI compensator. Also, you can select different type of modulator. For example, for the two-level boost rectifier, you can select, you can find different type of modulators. In the PFC topology, you can select the two-level boost rectifier and also the Vienna rectifier. In that case, I select the Vienna rectifier. And in the modulator for the Vienna rectifier, we have two options, the typical PWM and the space vector. So because in the Vienna rectifier is a three-level topology, so in that case, the modulator is a little bit different than the two-level rectifier. So for the main filter also you can find different type of solution, different type of main filter. For example, the L filter, the LCL filter, also the LCL with active damping. In that case, we are sensing the current through the capacitor of the main filter, and this is injected to the control structure. And also you can find the passive damping. In that case, we are taking into account a resistor in series with a damping capacitor. This network is in parallel with the capacitor of the main filter. So in that case, I select the filter. After that, if you select the DQ control, you can select two type of phase look and loop, the PLL. And also you can select different type of load, the simple resistor, the constant power load, or the current constant. Also, this is the option for the EMI filter. In the first example, I don't want to take into account the EMI filter, so I leave with this option, not applied. So if you go after that, if you go to this icon, this is the control structure. In the three-phase Vienna rectifier, we are implemented in DQ control. So we have two PI compensator for the DQ current. Also, we are implemented the coupling axis. This is for in order to compensate the gain of the modulator. Also, we have the part transform, and here we are implementing the DC link voltage balancing loop. So we are we want to equalize the voltage through the capacitors. This is the two capacitors. We are sensing each voltage, and we want to get an equalization by injected something like a common mode signal. After that, we have also an outer loop that controls the total output voltage. The output voltage at this point. So this output voltage is the sum of the two partial both cells. That means that we are summing the capacitor voltage, and that's it. So this is the control structure. Also, if you go to this icon, you can go to the power stage option. In that case, we can define the typical parameters, the grid voltage, the frequency, output voltage. For example, for the output power, I select in that case 15 kilowatts. Also, I want to change the capacitors, the capacitor of the output port. I select 1.6 millis, and in that case, I select 1 milli for the parasitic resistor of the capacitor. For the switching frequency, I select 50 kilohertz, and also for the inductance, I select 200 micros. Then I have to click on OK. After that, you can close this window. And now, if you go to this option, this is the phase looked loop window. In the phase looked loop window, you can select. Let me open the control structure. You can select with which axis do you want to align the grid voltage. In that case, for example, this is from the ED grid voltage. That means that EQ voltage will be equal to 0. So in that case, the output power is controlled by the D axis. So if I select the Q align with the EQ, so in that means that the D grid voltage, the D axis grid voltage will be equal to 0, and the power is controlled in this moment by the Q axis, as you can see here. Okay, for the PLL, also you can implement if you want to normalize the amplitude of the grid voltage, and I want to close the control structure. And also, if you go to this option, you can find the solution maps for the PLL. And if you go here, you can see the transient response for the PLL, and also you can select in this option. This is the transfer function, the transfer function graphics. In that case, you can see the transfer function. For example, if you want to see the open loop, the phase loop open loop transfer function, this is the pink trace. Also the plant, this is the green, and this is the brown trace is the closed loop for the PLL. And you can move the cursor through the solution map, and you can see how the body plots are updated immediately. So here in the phase look loop, also you can define manually the phase variant crossover frequency, also the stabilization time and damping ratio, and also you can put directly the parameters of the PI. So after that, I want to close this. And now it's time to define the current sensor. So for the current sensor, you have to go to this icon. And here you have different options. For example, you can implement a signal conditioning stage and also a low pass filter. You can define the parameters here. In that case, I select a unity feedback that compensate all the gains that we have in the sensor state, in the sensor chain. So for example, in that I put here 0.2 and bandwidth of equal to 30 kilohertz. So in that case, the unity feedback is simple, because just is 1 divided by 0.2 in order that the control see the actual value. The current is in actual value. That means, for example, if I have a 100 amperes in the power stage, also the control see 100 amperes. So that is the unity feedback gain. So in that case, I click on OK. After that, I have to define the gain of the grid voltage sensor. In this example, I select equal to 1. And also, it's time to select the output voltage sensor. In that case, it's very similar to the current sensor. We have different options, signal conditioning, and also a low pass filter. In this example, again, I select the unity feedback gain, and also, for example, I put a gain equal to 0.1, and also the bandwidth equal to 30 kilohertz. So after that, click on OK. And now it's time to, if you go to this icon, you can see here, this is the modulator. So in that case, this is the modulator for the three-phase, three-level rectifier for the Vienna. Also, here you can see the zero sequence signal here for the space vector, and this is the modulator. In this case, we have two carry signal. One, they are phase shifted 180 degrees. And also you can define the peak value of the carrier signal. So after that, it's time to go to the current compensator, inductor current compensator window. Also, you can open the output voltage compensator here. And I want to open the solution map for the intercurrent compensator and the solution map for the output voltage compensator. This is the transfer function. Also, I want to disable the transfer function for the PLL, and it's time. This is the TI represent the open loop transfer function for the current plan, and the purple trace represents the open loop transfer function for the voltage plan. So here you can move the solution map for the inductor current, as you can see, and you have also you can move the solution map, the point of the solution map for the outer loop. In that case, I select crossover frequency equal to 10 kilohertz for the inner loop, and also 50 degrees for the phase margin. And for the output voltage compensator, I select 50 degrees of phase margin, and also here I select 3 kilohertz for crossover frequency. So at this point, as you can see here, both control loops are stable. So now, as mentioned before, we have for the three-final rectifier, also we have another compensator window that it's called the DC-link voltage balancing. You can access to this icon, and here we have a third PI, and also we have a solution map for this PI. So if you click go here, this is the third solution maps for this PI, and also you can access to the transfer function if you go to this icon. The T represents the open loop for the DC link voltage balancing transfer function. And also you can see the plan and the closed loop. So for these control loops, I recommend to select, for example, 70 hertz for the frequency. The bandwidth of these control loops is very low, in order to not interfere with the main control loops of the converter. So after that, for example, let me put the TI. Okay, after that, it's time. You can go to the schematics for this option. This is a summary that show you all the options that you selected. So you can see we have a three-phase Vienna rectifier with L filter. We have the DQ control. Also, we have the DC link voltage balancing loop. We have the PLL. Also, we have the sensor chain for the current, the grid voltage and output voltage, and also this is the modulator. So after that, it's time to export this information. If you want to export, you have to go to this icon, and you can export to PSIM or to Simba. In the first example, I export to PSIM. I set a name that it's called example number 1. Click open, and now SmartCtrl is created the schematic simulation. So now in this version is a new way to the link with PSIM. Now we are using the Python. So you have to install for this export in order to export this template. You have to install the PSIM PI API from PSIM. But when you install this, you can export directly from SmartCtrl. So in that case, I want to put a simulation control. Here I reduce the time step to 0.5, for example, and also the total time. I want to increase a little bit the limiter of the PI for the anti-wind up. Maybe 3 by. Okay. So, and now I click on run simulation. So here we have the three-phase rectifier, as you can see here. We are sensing the voltage through the capacitor. We are assuming the capacitor voltage. We are controlling the total output voltage, and we have the two loops for the current, the axis and QR axis. Also, we have the PLL. This is the modulator and the sensor that we selected in the SmartCtrl. So I want to let me open the scene view. Okay, in the scene view, you can see that the control is stable. We have the three-phase current through the inductors. Also, you can see the voltage through the capacitor. And if you made a zoom here, you can see that both voltage capacitor are equalized. And also you can see, for example, the theta that it's measured with the PLL and something like that. So as you can see, the first example, the control loops is stable. So similar result we can simulate, for example, in Simba. If you go to Simba project, now I set a name for the simulation. Now we have to wait some seconds in order to SmartCtrl create the simulation schematics for Simba software. Now it's open. Okay. Now it's ready. So in the, maybe I can play that to run. In the Simba software, again, you can see here we have the three-phase Vienna rectifier. Also, we have the sensor stage that we define in the SmartCtrl. Here we have the control structure. We have the output voltage loop and the D current loop and the Q current loop. Also the modulator and the PLL. So here you can change the time step for the simulation and also the total time. So if you go to result, you can see, for example, the three-phase inductor currents. Also, I can add a new chart, for example, for the capacitor voltage. We can unify the two plots. And also, if, for example, if you want to see the modulating side. So you can see the result from Simba is very similar to PSIM, and also the control loops will be stable, are stable. So in that case, now the next example that I want to show you is for example, what happened if I select an EMI filter. So for example, I select the structure number 1, and now you can go to define the input parameter of the EMI filter. If you go to this option, click on here. This structure is composed by the one state of differential mode. Here, as you can see here, we have a capacitor and inductance, and also we can define the common mode choke here with this capacitor. We have a one state for differential mode and one state for common mode filter. So in the here we can define the values of the EMI filter. For example, I define 100 micros for the inductance. Here 1 milli for the resistance of that is in series with inductance. Also for the capacitor, I set 1 millis, and here for the capacitor value I set 4.7 micros. So after that, I have to click on OK. As you can see, the body plots doesn't change because this transfer function does not take into account the EMI filter. But if you go to this option, this is here you can access to the new tool that it's called the system level stability analysis. If you click in this option, you can see the both input, the both impedance. This is the input impedance for the PFC rectifier. This is a closed loop input impedance, and also you can see the output voltage impedance. Sorry, not output voltage. It's the output impedance of the EMI filter. So as you can see here, SmartCtrl predicts an instability in this case, because this appears at this message. So the system is unstable because it does not meet the gain Mayer criterion. That means that if you check the intersection between the both impedance, as you can see here at this frequency, I think it's this point, maybe 1, 2, 3. Yes, it's like this point. You can check the phase difference between the two impedance. So in that case, we are taking into account the phase of the output impedance minus the phase with the input impedance. So if this difference is less than 180 degrees, so the system will be stable. But in this case, we have a difference that it's greater than 180 degrees. That is why SmartCtrl tells you that this is an unstable cases. So in that case, I export this simulation to PSIM. Also, I put example number 2. Click to open. Let me close the simulation for Simba. Now we have to wait some seconds. And now I think it's ready. So we have to move here. I go to the simulation controls. And also I change the time step here. And again, I want to increase a little bit the limiter of the PI. Okay, and I can run the simulation. So in that case, we have the three-phase Vienna rectifier, and also we have the EMI filter that we selected in the SmartCtrl. So also appears in this simulation appears some parasitic capacitance. As you can see here, these values you can define in SmartCtrl in the EMI filter. If you go to the EMI filter, here you can define the parasitic capacitance. These parasitic capacitance are taken into account because we want to emulate the current mode, the common current mode. So now it's finished. If I, for example, plot the three-phase current through the EMI filter, as you can see, the system is unstable. That SmartCtrl predicts also the output voltage. And this is the three-phase current for the inductance. So one of the possible of the solution in order to that the system will be stable, we have to, for example, decrease the bandwidth of the outer loop. So in that case, for example, I move this to 1 kilohertz. If I move to 1 kilohertz, you can see here in the system level stability analysis tool that the SmartCtrl predict that the system will be stable. So only with this change, you can export directly to PSIM again and set a name that, for example, example number 3. Click on open, and now we have to wait a little bit. So now the simulation is ready. So we have to put again the simulation control. We have to reduce the time step 2.5, 0.1, and also we have to increase a little bit the limiter of the PI. And now it's time to run the simulation. So as you can see, it's the same simulation before. The main difference as that we changed the bandwidth of the outer loop. So we have to wait some seconds. and this simulation has to be stable. So this is the three-phase current through the EMI filter. So as you can see, the ripple is very low and the system now is stable. And also, if you want to see the three-phase current through the main filter inductors, this current has a more ripple. And also you can see the capacitor voltage here. So the two capacitor voltages are equalized. So in Simba, just we have the same result. Just to show you, maybe Simba number 2, open. We have to wait some seconds. Okay, so here this is the Simba simulation. I play to run. So here you can see this is the power stage. Also, you can see here the parasitic capacitor of some of the components. And also, this is the EMI filter. If you double click in this box, you can see here the one stage for the three-phase, the one stage of the common mode current, and one stage for the differential current mode. So, as you can see, if you go to result, here you can see, for example, the three-phase current. You can modify again. You can see, for example, the three-phase modulating signal, and also the capacitor voltage. Yeah, 1.5. So as you can see, the system is stable in Simba 2. So another thing that I want to show you, for example, that you can implement the control as mentioned before for the alpha beta pi current compensator. I select this option. The control structure change a little bit because remember in alpha beta domain, let me close this simulation. In alpha beta domain, the current reference are sinusoidal, it's not a constant value. So here, the output voltage, the PI of the output voltage impose the output reference. And with this expression, with this relationship, you can estimate the current reference for the alpha axis and beta axis, as you can see here. And here we don't have the coupling axis because this is just applied to the DQ control. And also you can see here we have the DC link voltage balancing loop, and that's it. And for example, we can export directly this option to PSIM, example number 4. Click open. Okay, again, we have to put the simulation control here. And also we have to increase here the limiter, and you can run the simulation. You can see here that we are implemented. Sorry, let me put. This is a current alpha. and current beta in that case. Now run the simulation. So remember, we have the output power here. With this expression, we are estimating the alpha beta current reference. So we have to wait some seconds. Maybe I can close this now. For example, the alpha current and alpha reference. As you can see here, the current alpha beta achieve the reference. And also, for example, this is the output power that is imposed by the outer loop. You can see, and the three-phase current also are stable. So for the alpha beta control, also you can implement the control loop, for example, the proportional resonant current compensator. Let me export this example. Okay, so the main difference is that in that case we are implemented the proportional resonant compensator, the transfer function you can see here in the inductor current compensator. This is a transfer function that is taken into account in the simulator, the simulation. So maybe again I can put a simulation control 2.5. Okay, and now click to run. In that case, we don't have a anti-wind up implemented here. Maybe we can stop back. We have to wait some seconds. Okay, and you can see the three-phase currents. The system is stable too. The output power and also the output voltage capacitors. So that's it. And for example, I want to close all the things here. For the three-phase Vienna rectifier, as mentioned before, you can select different type of LCL filter. The LCL filter, as you can see here, for the Q, here we have the third order pole, the third order transfer function. As you can see here, we have the resonant peak of the LCL filter. And also, you can, for example, in that case, if you select the active damping, as mentioned before, if you go to control, we are sensing the current through the capacitor of the main filter, and this current is multiplied by a gain, and then is injected to the control loops for the D axis and for the Q axis. And this gain you can change if you go to the power stage. You can change this gain here. That is these parameters with the key D parameter. For example, if I select 2, you can see if I've click on OK, you can see here how the resonant peak is attenuated. If I set 3, for example, click 3, it's more attenuated. The same things occur if you, for example, select the LCL filter with a passive damping. In that case, if you go to the power stage window, also you can define the passive damping network here, the values. For example, if I select 4 micros, you can see how the resonant peak is affected. So it's attenuated a little bit. So, and for the LCL filter, also you can select the same control structure as a L filter, and that's it. This is the most important thing that I want to show you about the new version of the SmartCtrl. So thank you for attending, and if you have any question, please write on the chat or let me know. Thank you.